Hi, my name is Amanda Lucini, and I am studying physics at Montgomery College.
Hi, everyone. My name is Marrufo. I am a rising senior studying electrical engineering with a minor in computer science at Cal State Long Beach. Go Beach.
All right, so in this talk, we'll be going over, we'll be talking about radio wave generation in a time-delayed narrowband optoelectronic oscillator. This summer, we were working at REU Photonic Systems Lab for Aerospace and Communication Engineering under the advisement of Dr. Timbo, Dr. Murphy, and Dr. Roy. So in this talk, we'll be covering a brief introduction to optoelectronic oscillators, stability analysis, numerical simulations that we did, and experimental methods and results. And finally, a discussion. So what are optoelectronic oscillators? So as the name kind of says, there's an optical part and an electronic part. And they are dynamical systems that consist of an optical and electrical path connected in a closed feedback loop with some non-negligible delay, T. So the first part of this loop begins with a laser, a continuous wave laser with a wavelength of 1550 nanometers. And this laser power is then sent into an MZM, which is a Mach-Zehnder modulator, which splits the power into two, as you can see the two P in. And there is on one side of the MZM a DC electrode, which takes in some DC bias. And on the other side, there is an RF electrode, which takes in an RF signal. And this is the equation that we studied and derived to describe the power output of the MZM. And as you can see here, there's the V of T from this part of the MZM, and then there is the V bias from this part. So next up, there is the delay line. So this is a fiber optic delay line, which provides the delay T. Moving forward, now you're taking your optical power and you're changing it to electrical signal. And this is the expression here is what conveys what is going on at this stage. And so the S in this expression represents the responsivity of the photodiode. So for some optical power in, you get some electric current out. And then next, we have a gain contributed by the low noise amplifier. And that is denoted as kg in the expression. And then this is passed through and filtered through a bandpass filter, cascaded bandpass filter, consisting of a low pass filter with a high cutoff frequency. So a low pass filter passes low frequencies, and a high pass filter which passes high frequencies. They're cascaded together, and here we have some of the some important details about it. So this expression here conveys what's going on at this point in the loop, and we're setting that equal to the previous expression to indicate that that is being input into the cascaded bandpass filter. We can measure the RF signal on an oscilloscope. And finally, we close the loop when we input that RF signal back into the MZM at this part here. So
least I can see. Awesome. So now turn that on. We're going to do some work on stability analysis. Cool. There's the mic. So let's build some intuition. What is stability analysis? Let's give a real world example. Over here on the left, we have a ball on a hill. Now imagine we give that ball a small push. We can see how gravity is going to cause the ball to come down the hill faster and faster. That's actually an unstable system. Whereas on the right, if we have the ball sitting at the bottom of a hill and we give it a tiny push, well, it's just going to come back to rest. That's a stable system. And so we can define this mathematically using something called perturbation analysis. So we have this delta x, which is the change response to that perturbation. And we're saying it's proportional to an initial push, that delta x naught, times an exponential. And we know exponentials. We know that in this case, lambda determines the stability of our system. If we take the real component of lambda, and if it's positive, then we have a system that is exponentially growing. That's unstable. If we have a real lambda part that is negative, then it's going to exponentially decay. That's stable. So we have this equation that we derived from the model. We're going to make it a bit easier to work with. We're going to do a couple assumptions, a couple substitutions here, and we're basically going to take this x of t and use it to represent the VRF voltage. We have this phi component, which is just the phase shift in our modulating signal. And finally, we have beta, which is the open loop gain. Beta is going to be important. When we rewrite this, we get this much simpler equation where we have omega naught, which is just the center frequency of the bandpass filter. We have delta omega, which is the bandwidth. And then we have this x of t, which is just a delay. So now let's talk about how that open loop gain contributes to stability. We did some derivations to find what's called a Hopf bifurcation, where the system transitions from stable to unstable. And we found that it occurred at this critical open loop gain beta CR, which is -1 over sine 2 phi. Well, what does that mean for us? It means for our oscillator, if we want to oscillate, we want to have an open loop gain that is greater than this value. We want it to be unstable. So we use a phi value of -pi/4, which means our beta critical is now 1. So basically, we want an open loop gain beta to be greater than 1. That's our goal, and we should see oscillations in that case. So we did some numerical simulations to show that. We did a fourth order Runge-Kutta method, which is really just a fancy Euler's method. These are some of the parameters, the bandpass filter center frequency, the bandwidth, the time steps, all that fun stuff. The two important parameters to pull from this is our phi, -pi/4, makes things a lot easier, and our beta for the last simulation is 2. So first, we start with a phase portrait. A phase portrait shows how a system changes from an initial state and how it basically adapts its state over time. So we have a system with this open loop beta, which is before the Hopf bifurcation, and we see it starting at this pink arrow. As we transverse it, as we go towards the end, we notice that it actually converges to a focal point at the center. That's stable. Now, if we make beta past this Hopf bifurcation, this open loop gain, we see it just oscillates. It doesn't come to that focal point. This is unstable. This is the behavior we want in our system. So we simulated that, and this is what we got with beta is equal to 2. We got an oscillation at 21.3 megahertz. Note that our bandpass filter center frequency is 21.4. And for our experimental setup, this is the RF output that we're going to measure and compare it to. And with that, I'll pass it back to Amanda.
All right, so for our experimental methods and results, this is the lab setup. And as you can see, there's the delay line. It's a delay spool of 4.2 kilometers long. So we started with a laser, again, 1550 nanometer wavelength, and we set it to 100 milliamps. Then we have a polarization controller, a variable attenuator, which attenuates power by some -20 decibels. And finally, there was the fiber optic splitter or coupler, which, without getting into too much detail, basically just helps with fine-tuned measurements of the attenuation and being able to attenuate it in like a more precise way. Next, and this part was proved to be very, very important, was the low noise photoreceiver with a transimpedance amplifier inside of it. And this is again referring back to like the previous diagram was where you take some optical power and you're converting it to electrical signal. But in this case, the responsivity S was about 40,000 volts per watt. So pretty powerful and very helpful in maintaining the linearity between the optical power to electrical signal conversion. So then we also have a narrow band pass filter, narrow because the band of frequencies that is allowed through this filter is quite narrow, as you can see with the bandwidth of between 19.2 and 23.6 megahertz. And as was mentioned before, the center frequency is at 21.4 megahertz. So there were some key questions that we had to ask while working in the lab in order to, well, our goal was to see oscillations. So first, we need to account for the power losses in the system. And so we used an optical power meter to measure the power at various points in the loop and to see, how much loss there was between, connectors or between different parts and if it was reasonable. So for example, the delay line, the expectation is a 0.2 dB loss per kilometer. And we saw roughly about that much. So the next question is also, is the optical power input proportional to the RF power output? In this case, we used an open loop test using a waveform generator to input the RF signal into the MZM. So we know the frequency as being 19.4 megahertz and the amplitude of 250 millivolts peak to peak. And we can basically just see, we can measure here, as you can see, we can look at the oscilloscope and giving this test signal B in, what kind of B out do we get? And by doing B in over B out, we can measure the open loop gain. And again, notice how the loop is broken. That's why it's called an open loop. All right, so we did see oscillations, and that was the goal. Our beta was approximately 2. The frequency of our experimental oscillator was 22.8 megahertz. And moving forward, Marco will discuss this a bit more.
So yeah, those are our results, and I think we are kind of running low on time. So you'll notice we have a difference between the experimental and the simulation. I urge the audience to ask why in Q&A.